At the beginning of this chapter, I told you that the Carnot cycle and also the gas power cycle or reverse Carnot cycle is not an appropriate cycle or to be an ideal cycle for refrigeration system. Then we have started to discuss to introduce the vapor compression refrigeration cycle. But if you remember, I told you that this reverse Carnot cycle actually is called, it can be a refrigeration cycle, which we call that gas refrigeration cycle, which is generally or basically a reverse Brighton cycle. A reverse Brighton cycle, which is the gas refrigeration cycle, actually, can be used for refrigeration as this cycle is the Brighton cycle, which you already know about that in previous chapters, which is the ideal cycle, which is a cycle actually for the gas power systems or gas power cycle. For gas refrigeration cycle, we have reverse out there, right? We call that reverse Brighton cycle. And the only difference between this cycle and Brighton cycle is the direction of the working fluid. We have again here two heat exchangers. In this case, for the reverse Carnot cycle, the flow of working fluid, the direction is from compressor to the turbine. As you can see here, we have two heat exchangers. We have compressor and we have also turbine in our cycle. The W net or the work here is given to the compressor to compress the working fluid, which is air in this, which is the gas phase in this cycle. It is compressed in the compressor. It will go to the heat exchanger. The heat is rejected to the warm environment. After that, it will go to the turbine, and in the turbine it is actually an expansion, something similar to the expansion valve. Then due to the in the turbine, the temperature of the working fluid, which is the gas, will reduce, and after the turbine it will go to the heat exchanger. After turbine we have a low temperature gas and it will go to the heat exchanger, and in this heat exchanger the QL or the heat is transferred from the cold refrigerated space to the working fluid. Excuse me. And then again the cycle will continue. The gas will go to the compressor and the cycle will continue and repeated by this. We call this reverse Brayton cycle. And also you can see in the TS diagram state 1, state 2 in the compressor. Excuse me, it is compressed. The gas is compressed in the compressor. And for an ideal reverse Brayton cycle, we can assume it is a constant, it is isentropic compressor. And from state 2 to state 3 in the heat exchanger, we have heat rejection. From state 3 to state 4 in the isentropic turbine, we have temperature reduction. And from state 4 to state 1, the heat is transferred from the cold refrigerated space to the working fluid. And again, this cycle will continue. You can see here this cycle compared to the vapor compression refrigeration cycle, it is more simple, and also you can see here the component are less than the component which we had for the vapor compression cycle. To calculate COP or coefficient of performance for this reverse Brayton cycle, again we need to divide QL divided by W net in. Desired output given input QL is the desired output of the cycle, which and also W net in is equal to W compressor in minus W turbine out. In other words, the W net for the whole cycle is the W net which is given to the compressor, and W which is delivered by the turbine. Here is a reverse Brayton cycle. The purpose is not to produce power. The power is given here to the cycle to absorb thermal energy from the cold refrigerated space. And QL here simply is equal to H1 minus H4. Here QL is uh, sub Q actually, because here we do not included the mass flow. QL is equal to H1 minus H4. W turbine out is H3 minus H4 in this process, and W compressor in, or the power input for the compressor, is H2 minus H1. A substitution of these enthalpies in this COP, we can calculate the COP as well. If you want compare the COP of the reverse Brayton cycle or gas refrigeration cycle. So from now on, reverse Brayton cycle and gas refrigeration cycle are identical. So the COP of gas refrigeration cycle is generally lower than the COP of the vapor compression refrigeration cycle. And even the COP of this gas refrigeration cycle is less than COP of the reverse Carnot cycle. The reason is here in this TS diagram. This cycle 1A3B is the reverse Carnot cycle. The area on the cycle, as you know, in a TS diagram, represent the required input for that cycle. So you can see here the area for 1A3B is smaller than the area for the gas refrigeration cycle, which is 1, 2, 3, 5. You can see this area is much less than this whole area. So it needs a lower amount of the work input. In addition of this advantage, or this reason for the higher COP of the reverse Carnot cycle compared to the gas refrigeration cycle, the refrigeration amount also for the Carnot cycle, reverse Carnot cycle, is higher than refrigeration amount of the gas refrigeration cycle. In the TS diagram, the area under this process from 4 to 1, which is in the turbine, which is in the process 4 to 1, is in this heat exchanger. It is amount of QL. So the area under this process is amount of the QL, or the amount of refrigeration. In the gas refrigeration cycle on the TS diagram, it is area under this cycle. So this is amount of QL for the gas refrigeration cycle. But the amount of the QL for the Carnot cycle is from B to 1, which also it includes this. So this triangular shows the difference between the refrigeration amount of the reverse Carnot cycle and gas refrigeration cycle. And you can see here that the COP of the gas refrigeration cycle is not that much high, even less than the reverse Carnot cycle. So you can see here, it is not that much efficient, this gas refrigeration cycle. So where and why we need to use this type of cycle? As I told you, we have uh, uh, less number of the component for this cycle, and also it has some advantages which make it an appropriate refrigeration system or cycle for aircraft cooling. This is due to its simplicity and also its lighter component. For aircraft, as you know, the weight is one of the most important properties. So due to the lightweight of this cycle, it is a common method for the refrigeration of the uh, different airplane. However, to improve the efficiency, we need to add a regenerator to the cycle. Without regenerator, the efficiency of the cycle depends on the temperature of the surrounding. If you notice in the cycle here, the temperatures which we have here in especially in state one and here, you know, this is what we have uh, in an airplane. We have compressor, turbine, W net is given to the compressor, then it is compressed, it goes to the heat exchanger, the temperature, the heat is rejected to the surrounding, and then it will go to the working fluid will go to the turbine, and cool air output is delivered, which is used to reduce temperature inside the cabin of the airplane. So what you can see here, the temperature here, especially here at the entrance of the turbine, will determine the temperature after turbine as well. So if we can reduce temperature here at the entrance of the turbine, we can improve the efficiency or COP of the cycle or provide cooler air at the exit of the turbine. So we add also regenerator in the cycle. And now we are going to show you how this regenerator can improve the efficiency or COP of this cycle and provide cooler uh, air to for the air conditioning of the airplane. Without regeneration, the lowest turbine inlet temperature is T0. T0 is the temperature of the surrounding or any other cooling medium. With regeneration, the high pressure gas is further cooled to T4 before expanding in the turbine. In other words, before this. So lowering the turbine inlet temperature automatically lowers the turbine exit temperature, which is the minimum temperature in the cycle, which we can reach, and also it can be used to cool down the air inside the airplane. So how this regenerator works? Similarly, we have again a compressor in this gas uh, uh, refrigeration cycle. The compressor goes to a heat exchanger. Heat is rejected to the warm environment. Here the gas is compressed from state in the compressor. It goes to the heat exchanger. The heat is rejected in the constant pressure process. Then we have added this regenerator. Again, it goes to the regenerator. More heat is rejected to the surrounding, but this time not to surrounding, it is rejected to the regenerator. So the air which is provided for the turbine or the gas that is provided for the turbine or is even more cooler. And again, notice here the regenerator is considered as an adiabatic regenerator, and all of the Q or heat is transferred from this line to the what is uh, coming back from the turbine. So here, after this regenerator, it will go to turbine, it will expand and provide, in the turbine, it will provide, it is expanded, the gas is expanded, and as you know, after expansion of the gas, its temperature is also reduced. So after turbine, we have low temperature gas, and this low temperature gas can be used in a heat exchanger to absorb heat from cold refrigerated space. Then again, this gas will go back to the regenerator. Here, the Q, which is rejected from the first line, is absorbed in from the well, is absorbed by the air or the gas which is coming back from the turbine and heat exchanger, and it will go back go back to the compressor. This regenerator will help to reduce the temperature at the entrance of the turbine, which it will cause the reduction of the temperature even after turbine, and will provide a cooler gas for in this heat exchanger, which is going to be used for the cooling the environment. How this regenerator can help also, here you can see, the gas which come back from this turbine and this from this heat exchanger, the temperature of the gas in this line is lower than this line. So here we have high temperature or higher temperature gas. Here we have lower temperature. So in TS diagram, if you want to show this cycle, is like from state 1 to state 2, we have compressor, isentropic compressor. The gas is compressed, then its temperature is increased. To reduce the temperature, we introduce it to a heat exchanger from state 2 to state 3. And also we have here the regenerator. Then from state 3 to state 4, we reject more heat from the working fluid. So from 2, 3, 4 is in the heat exchanger and in the regenerator. In the state 4 to 5, we have turbine. In turbine, it is expanded. The gas is expanded, and the temperature is reduced from state 4 to state 5. This is the minimum temperature which we can reach, and it will go to the heat exchanger, and in the heat exchanger the heat is the Q is absorbed by the gas and its temperature is increased, and this cycle will continue. You can see also from stage 5 to stage 6 we have this heat exchanger. The temperature of the working fluid is increased in this heat exchanger, and the rest of increase in the temperature is in the stage 6 to stage 1 in this process, which is in the regenerator. Based on your information from previous chapters, and especially related to the gas power cycle, you know that this amount of heat which is uh, absorbed is amount of this Q, which is a QR here to this uh, and QR here. This in this actually in this QR is rejected. Here QR is absorbed. The coming back from 6 to 1. So the heat which is rejected here is absorbed here. So totally, regenerator just uh, absorb energy in some part of the cycle and release it in another part of the cycle. And by this, it will improve the COP of the whole cycle, which is a desirable characteristic for a refrigeration cycle.